Welcome to EPG Pathshala for this course on computer networks. So in this module we will be looking at the IP protocol, we will be looking at how subnetting and CIDR are handled. So we will start with IP addressing and how subnetting is handled in IP. We will look at how subnet masks are handled. We will also look at how classless addressing happens, that is the CIDR addressing and the CIDR masks. So we will also look at how that is used for forwarding and aggregation, and then we will also briefly touch upon network address translation. So we have already looked at class based IP addressing, where we have seen that it has class A, class B, class C and class D and E addresses. We know that class A addresses are have only 7 or 8 bits for the 7 bits for the network part, and the rest of the bits are for the host part. Class B has 16 and 16, class C has 24 and 8. So basically class C addresses are used for small networks because it can accommodate only a small number of hosts. Class B addresses are used for medium sized networks, it can accommodate a medium number of hosts, and class A is for large networks. So this is typically how the class based addressing is done to take care of these small, medium and large sizes that you have with respect to networks. Okay, so let us look at how we could add one more level to this hierarchy, and that is what subnetting is all about. So for instance, we just talked about having a network part and a node part. So now we are saying we will add one more level to the hierarchy, which is called as a subnet part. So between the net and the host, we are bringing in another level of hierarchy called the subnet or a subnetwork. Okay. So now what we will be doing therefore is, if you take the full 32-bit address, we will divide it up now into 3 parts: a network part, a subnet part and a host part. So now you can see that we are introducing one more level into this hierarchy, and what is the advantage of doing this? Basically it will allow us to have a better use of the address space. So we will look at how that happens. Okay. So let us first understand what we mean by this subnet part of subnetting as such. Okay. So if you look at an IP address, we said we have a subnet part and a host part. So basically what we are trying to do is, whatever we have in the host part in a normal IP class B or a class A address, we are trying to split that further into a subnet part and a host part. So the higher order bits will be used to indicate the subnet part, and the lower order bits will indicate the host part. So if you take for instance an example a network here which is shown here, which consists of say 3 different networks, so 3 sub networks so to say. So that is, if you see, I have a router here or a switch to which there are 3 interfaces, and on the 3 interfaces there are 3 different networks which are connected. Okay. So you can see that if you look at the addresses that are assigned over here, all these addresses will have the same prefix. So if you see here, you have 223.1.3.27, this is 1.3.1 and this is 1.3.2. So up to 223.1.3 you can see is common for all the nodes which are there in this subnetwork. Similarly, you can see in this subnetwork they have a common prefix which is 223.1.1, right, and this has similarly 223.1.2 and so on. Okay, so what exactly is a subnet? You can look at it typically as something which kind of interfaces to one part of a router, and for which this initial part of the IP addresses are all the same. Physically, you can also look at it as something as a network, which if you kind of disconnect from the intervening router, it will still physically be connected to each other. So that's typically how we identify or kind of designate these subnetworks. Right. So now, what do we have to do in order to do this subnetting? So if I want to determine, for instance, how exactly this, which are the nodes which can be formed into a subnet, one way to do that would be to just detach each interface from its host. Okay, and you will create, for instance, from this, so you are kind of detaching this interface, you are detaching these interfaces. So now what happens is that this becomes an isolated network, this will become an isolated network, and this becomes an isolated network. So you can see that these isolated networks are what we will be referring to as the subnets or the subnetworks. And for each isolated subnet now, okay, each isolated network now, we call this as a subnet, and for this subnet now we need to figure out how the addresses can be assigned. Okay. So we will just take a look at an example and get a better feel of how this whole thing basically looks like. So I have a router R1 here, and there are 2 networks which are connected to it, the 2 interfaces. So this itself can be one subnet and this is another subnet. You can see that the common part of the addresses over here are 143.123.1, right, that is common part. So that we call as a subnet, and we say that the subnet address is 140.123.1.0. So similarly, if you look at this subnet here, you can see that R1 is connected to 2 other routers, R2 and R2, through its interface and through a particular network over here. Now, so this network you can see has 3 interfaces, one connected to R1, one connected to R2 and another connected to R3. But if you look at the addresses, you can see that there is a common part there, which is 140.123.1.250. So that becomes the subnet address for this particular subnet. Similarly, you can see that for this at subnetwork which is connected to the other interface of R2, you have a common part which is 140.23.2. So here similarly it is 140.23.3, right. So this is typically how the subnet addresses will be assigned. Okay. So how do I specify which part of the address actually becomes a subnet part and which part actually becomes the node part of the address? So this is done by having something called a subnet mask. So the idea of having a subnet mask basically is to be able to specify variable partitions of the host part of the address. So if I take a class A address or a class B address, we know that a class B address for instance has 16 bits for the network number and 16 bits for the host number. So what we want to do now is we want to take this 16-bit host number which can accommodate 2 power 16 hosts and divide that into multiple subnetworks, each having a smaller number of networks. So that is what we want to do. So in which case what we would actually like to do is we would like to treat the network part plus the subnetwork part as corresponding to the network address and the rest of the bits corresponding to the node part of the address. So in which case this wherever I have the network number and wherever I have the subnet ID, these two together have to be identified as belonging to a network part and the rest of the bits will have to be referred to as identifying the host part, and this is what is specified by means of a subnet mask. So the subnet mask you will see will have all ones in the places which correspond to a network number, that is all the bits of the 32-bit address which correspond to the subnet to the network number and the subnet ID will be marked with all ones. Okay, so you can see that in this case if the subnet mask here indicates that I have all ones in the first 8 bits, all ones in the second 8 bits and all ones in the third 8 bits, which in our dotted decimal notation will be represented as 255.255.255.0. So this you can see this, the first 3 255s refer to the fact that the first 24 bits are ones and the last 8 bits are 0. So this part becomes the host part of the address and these other bits that you have here, they denote the subnet part of the address. So in this example you can see that you actually have a subnet mask which takes this class B address and identifies that these 8 bits, the first 8 bits of the host part will be used to identify the subnetwork. Okay, that will be used as a subnet ID. And you can see that with this kind of a subnet mask, because I have 8 bits for the subnet ID, you can have 2 to the power of 8 different subnetworks, which is 255 different subnetworks. So this subnet mask actually tells us that you have divided this class B address into 255 different subnetworks, each subnetwork having 255 different nodes or 256 different nodes, node addresses, of which about 254 are actually usable because we don't because all zeros and all ones are normally special addresses. So you will have about 254 usable addresses. So that is what we do with the help of the subnet mask. So it is very important to understand how this subnet mask basically works. It is basically specifying which bits have to be treated as network part and the subnetwork part. Okay. So once we have the subnetting in place, how is the forwarding going to become different? Okay. You can see that the subnetting basically will come into play only at the edge router. As far as the rest of the routers are concerned, they will still treat it as a class A address or as a class B address. Okay. So if you look at a class A or a class B address, okay, you will find that if you take a look at for instance a class B address, you have the 16 bits for the network part of the address. So the entire network part of the address will be treated as the network address at the core routers. But the moment we come to an edge router, okay, so what we have to do there is, now let us say for instance we come to router R1, okay, some packets have come to router R1. So when a packet comes to router R1, we have to figure out whether it has to be sent out on this subnet or that it has to be given to this subnet. So now what we actually have to do is, given an address, right, so we need to apply the subnet mask, the appropriate subnet mask, and once you apply the subnet mask, you have to figure out whether it matches with that corresponding subnet number. If it matches, then you forward it to that corresponding interface. Okay. So for instance in this example, at router R1, we can see that these two nodes here have an address of 128.96.34.15 and this has an address of 128.96.34.0. So let us say the subnet number is 128.96.34.0 and the subnet mask is 255.255.255.128. Now I have already explained what a subnet mask means. Let's now take a look at what we mean by subnet number. Now what we mean by subnet number is that this part is the common part, the network number part for all the nodes which are there on this subnet. Now how do I arrive at this number? If I take any of the addresses, complete addresses that I have on the subnet, and if I apply this mask, when I say apply the mask, what we mean by that is that we are doing an AND operation. We do a bitwise AND operation. So when you do a bitwise AND operation, so what you will be left with is that you can see that since we are ANDing with all ones and zeros, the portion which is ones, which corresponds to the network part of the node and the subnet part, that will be isolated, and the node part of the address will be blanked out, will be zeroed, right. So you identify the network and the subnetwork part put together, that becomes the subnet number. So in this case, if I apply this 255.255.255.128 as the mask, you will find that you get 128.96.34.0 as the number for the subnet. Similarly, if you look at this network over here, you will see that the subnet mask here again is 255.255.255.128, and if you apply this mask on both these addresses, the address that you get, the subnet number you will get will be 128.96.34.128. That is, up to 25 bits will be common as for both these addresses. Okay, the first 25 bits are in common, and that will turn out to be 128.96.34.128. This 128 indicates that it is the first bit of the last 8 bits, which will be a 1. That indicates that that will be included as part of the subnet address. Okay. So you can see that the entries that we have at this router will be like this. So you will specify that if the subnet mask of 255.255.255.128 is applied and the subnet number turns out to be 128.96.34.0, then it has to be sent out on interface 0, right. So it goes on this interface. Otherwise, if you apply this mask and you get this subnet number which corresponds to this other network, then you send it out on interface 1. Okay. And you could have another one which says that if it belongs to 128.96.33.0, then you send it out, you have another subnet mask which is 255.255.255.0. If you apply this subnet mask and you get this address, then it is said to be sent out to next hop, which is R2. So it will have to be sent out through this through an interface to the next hop address, which is R2. So this is basically how the forwarding table at the edge routers will now start looking at. Earlier, remember, when we looked at routers, we would only have had the network number and the next hop information. Now we have one more piece of information, which is the subnet mask and the subnet number. Okay. So now if you look at the forwarding algorithm with this in place, you will see that pretty much whatever we talked about now is what will be done as part of the forwarding algorithm. If D is the destination IP address, so what do we do? For each entry, you do an operation of ANDing the subnet mask with the destination address. So for each entry which corresponds to subnet mask, subnet number and the next hop, you calculate a D1 which is subnet mask ANDed with the bitwise AND operation. Now if D1 is equal to the subnet number, so then, and if next hop is an interface, then you deliver directly to that destination. Else you deliver the datagram to the next hop, which could be a router. So this is basically what will happen. Okay. Now if nothing matches, normally it will go to a default router. So that is what we normally do, right. If there is no match, it just goes to a default router. Okay. Now there are certain interesting things to remember with this idea of subnetting being used. Now it's very interesting to note that it's not necessary for all the ones in the subnet mask to be contiguous. So in the example that we looked at, we said that the first 25 bits were 1 or the first 24 bits were all ones, indicating that the subnet mask had all contiguous ones. That is not actually necessary. You could actually have any portion of the node part of the address specified as a subnet mask, as a subnet. So you can kind of divide the network in different ways. So there are some interesting configurations that you can actually work out if you divide it differently. But of course, for ease of operation, we normally keep it contiguous. And you can also put multiple subnets on one physical network. In fact, in the example that we looked at just now, we had two physically different subnet networks and two physically different subnetworks also. That is not necessary, it has to be that way. What we could also do is, you can have multiple subnets belonging to the same physical network. By having different masks, you can actually identify them. Okay, that is also possible. Okay, and another point to note is that the subnets are normally not visible from the for the rest of the internet. It's only at the local edge router that the subnetting is handled. So the subnet is something which is useful when you have, for instance, one class B address and you want to share the class B address among multiple subnets, and you want to keep these subnets, these different networks, as separate networks at the local end, at one end, at an institution end, or at a organization end, or something like that. But the rest of the world, you want to expose it only as a single address. So in those cases, you will find that the subnetting is a very ideal method of dividing the network into multiple smaller networks. Okay, so this is something that has been used for effectively sharing the addresses and so on. Okay, but in this classful addressing that we have been looking at so far, okay, there are some problems that have been identified. So one of the problems that we talk about when we talk about this classful addressing, that is when we have class A, class B and class C and so on, these fixed kind of addresses, it leads to some inefficiency in the use of the address space. So let us look at where this inefficiency basically comes from. So if you look at class A addresses, for most practical address networks, you will find that a class A address is too large, because remember, class A address can accommodate up to 2 to the power of 24, right? It is about 4 million nodes. So with 4 million, you are normally not going to have that big number of nodes in a single network, okay? And a class C address is normally too small, because class C can accommodate only about 256. So you would normally opt for a class B, which can accommodate up to 16K. So what if I really don't need 16K, right? I will still be opting for a class B network. So is it really useful, right? Am I really using all the addresses that have been allocated to me? So that is where basically a problem arises. And there are also other scalability concerns. Now what happens is that if let's say I require 1024 addresses, I may not opt for a class B address, but I may opt for 4 different class C addresses, because each one will give me 256. So 256 into 4 will give me about 1024. So in which case I will have multiple class C routing entries to come to the same same network, because this network is having about 1024 nodes in it. Okay, so you have this problem of this 32-bit address space getting exhausted. So that is something that we really need to handle. Okay, actually, can you guess which class of IP addresses would have neared exhaustion faster? It would be class A or class B or class C. If you think about it, you will see that it is the class B that has got exhausted faster, because A is too large, so you do not pick up an A address, class A address. C is too small, so you do not pick up a class C address. So most people will be picking up only a class B address, right? So you kind of pick up class B addresses again and again, and therefore you will end up having you are coming to this problem of exhaustion of all the class B addresses that are available. Because remember, we have only 2 power 16 different class B addresses, so they get exhausted quite quickly. So this is a problem that the internet actually has run into over the years, and there have been solutions that have been proposed for this particular problem. So that is what we need to be looking at. Now to understand the demerits of this, we talked about this address, about this exhaustion problem, right, and about the inefficiency in the address assignment. So just to understand that, let us just take a look at a simple scenario. Okay, suppose now basically what is happening now is that if a network requires, let us say, only 2 hosts, okay, it requires only 2 addresses. So what will it take? It will have to take a class C address, because that is the smallest chunk we get, right. So you get about 256 different addresses. So you have to take a network, class C network, which actually has 256, but you are using only 2 out of those. So 2 out of 255, that is about 78.78, 0.78% efficiency. Okay, so let us say, for instance, you want 256 hosts. For 256 hosts, you will have to choose a class B address. So if I choose a class B address for a 256 host network, so what will be the efficiency? You can see that there are actually 65,535 nodes available, addresses available, of which only 256 are being used. So you can see that the efficiency of usage of those addresses is only 0.39%. So we can see that this address assignment efficiency is very, very low when we opt for larger networks, even though our requirement is small. But we are forced to opt for these networks because the network addresses are handed out only in these fixed size chunks. You either get a 256 size network or a 64K network or a 2 power 24K network. Okay, so this is a problem that definitely was something that the entire internet world was facing. Okay, so what is the solution that people came up with for this? So one of the first solutions, a kind of a brute force kind of a solution, is that you say, if anybody asks you for just for a class B address, even though they are not really close to 64,000 addresses, do not grant them one class B address. You just say no to giving addresses to an autonomous system, or a domain which is asking for a class B address, even though it does not have really 64,000 different addresses that it actually needs. So that is one solution. Or another solution could be that you will just you give them an appropriate number of class C addresses. As I just mentioned, if I want 1024 addresses, you take 4 class C addresses. So that is an option. But we already saw what the problem with this kind of a solution is. The problem is that you will require excessive storage at the routers, because if I say for instance I had 8000, so 8000 nodes is what was my requirement. I will have to be given 8 into 4, 32 different class C addresses for that. So there have to be 32 entries in the routers for this single network, right. So that is how it will be. So similarly, if you had say for instance 16 class C network numbers assigned to it, so every internet backbone router would require 16 entries in the routing tables. So this is how, even though the path that is taken by for each of these networks is the same, you will still have 16 different entries. So that is something which is not really desirable, because this leads to increase in the number of entries, and that obviously as the number of nodes increases, as the number of IP addresses increase and so on, will make the process of looking up at the routers slower. Okay, so that's a problem. And of course the second problem that we saw is that we have already seen that there is a address assignment inefficiency. Okay, the efficiency will be only about 6.2% in this example. So that is also not something which is desirable. Okay, so what do we do, right? So what we would like to do is, we would like to go in for something called a classless routing mechanism, and this is the solution that has been proposed and that is currently in use. Okay, so if an autonomous system or a domain requires say 16 class C network numbers, okay, so instead of giving it out 16 addresses at random, so what you would do is, you give it out a block of contiguous class C addresses. Okay, so these addresses are kind of blocked together. Okay, so once that happens, so for instance, so let's say for instance I am giving addresses 192.4.16 through 192.4.31. Okay, so you can see that 16 to 31, these last few numbers that we have here, they are contiguous numbers, right. So this indicates 16 network addresses which are contiguous. Okay, so if you look at the network addresses now, you will find that the top 20 bits of all these addresses, right, 192.4.16 through 192.4.31, the top 20 bits, we know that you can easily see that the top 16 bits are the same, right. If you look at 16 through 31, you will find that the first 4 bits of these are also the same. Okay, so you will find that 16 plus 4, 20 bits of all the addresses in this range are all the same. Now what we do is, now since 20 bits are the same, we now create a network which has 20 bits identifying the network number. Okay, right. So this becomes our new network number. We say that this number here, right, which is 192.4.0001, right, followed by zeros here. Okay, that becomes our new network number, and we are identifying by using a 20-bit number. Now you can see that this is between a class B network number and a class C network number. A class B network number will have 16 bits, a class C will have 24 bits. So we have between 16 and 24, we have created a new network type which has 20 bits, right. So what we are basically going for is, we are going for a classless addressing scheme. So don't have classes and say I will give it out only in chunks, but have the flexibility to determine how many bits we will use for the network number and how many bits we will use for the node number, for the number of nodes, right, for the node part of the address. So once we have that flexibility, we can now start assigning addresses as required, right, in the number of chunks that are required, instead of having these fixed size chunks. So that is the idea that is used in classless routing. Okay, and how do we specify this information, that this part belongs to the network part and that part belongs to the node part? We take the idea from our subnet mask. So we have seen that we can use these masks to identify which part corresponds to the network part and which part corresponds to the node part. So that is what we use over here. So now we say that this many bits, right, these many bits, the first 20 bits, they will be used as the 20 bits or 23 bits, they will be used as the network part, and the rest of the bits will be used as the node part. So you can specify that by using these masks, right. So if you have an address format which says a.b.c.d in our dotted decimal notation, you specify -x, and where x is the number of bits in the net and subnet portion of the address. So this is what we have been using. Now this is what we will use in our classless addressing mechanism as well. Okay, so if you look at this classless addressing mechanism, you will see that there are a number of advantages that we will get. First is that it will minimize the number of entries that are there in a router, and also minimize the number of routes that a router needs to know against the need to hand out addresses efficiently. Okay, rather it kind of balances these two different goals that we had. Okay, we saw that we need to reduce the number of entries in the router, and we also would like to have good address efficiency. That is both of these we are trying to achieve with this classless addressing scheme, and this is called as CIDR. It's called as classless inter-domain routing mechanism. Okay, and this CIDR mechanism also allows us to aggregate the routes. So, you can use a single entry in the forwarding table to tell the router how to reach a number of different networks. Okay, and so it breaks the rigid boundary that we have between the different address classes. So, it gives us a much more efficient addressing scheme. Okay, so let us look at how exactly we assign these addresses, okay, a little bit more in detail. Okay, the first thing we need to understand is that when we are assigning these addresses, the addresses assigned have to be contiguous blocks, so that you will be able to identify a shared common prefix between those different blocks of addresses. Okay, and the convention that we normally use is that we place this slash and we place a number which indicates the length of this prefix. That tells you if you have an address which says 192.4.6/20, it indicates that out of this of the entire address that we have, 20 bits will be used as the network part of the address, as the CIDR mask, right. So, you will have 20 ones in your mask, in your you can call that now, instead of calling it as a subnet mask, we call this now as a CIDR mask. CIDR is pronounced as CIDR, and we say it's a CIDR mask. So, the CIDR mask now will have 20 ones starting from the first bit, from the most significant bit. Okay. So, in this prefix based addressing mechanism, if you want to specify a class C, a normal class C network number, which actually has 24 bits long network address, you could write it as 192.4.16/24. So, you can see that these two different numbers here, right, by means of this prefix length being specified being different, actually refer to two different networks. Okay, this refers to a 192.4.16 network where 20 bits will be used as the network part of the address. Here it is 192.4.16 where 24 bits will be used as the network part of the address, right. So, you can see that by specifying the prefix length, you can vary the number of the size of the networks that we have, and you can accommodate different sized networks. Okay. So, this is something which is very, very interesting. Okay. So, a class B network similarly would be written as x.y/16, y/16, because a class B network basically has 16 bits in the network part and 16 bits in the node part. So, in the CIDR addressing scheme, a class B network would be represented like this. Okay. So, now let us look at how the routing will become different once you have this kind of a CIDR based addressing. Okay. So, when you have CIDR based addressing, what we require the routers to understand is that they have to know how to handle these classless addresses. Now, to handle the classless addresses, what is important is that it must understand the network number, and it must understand that the network number can be of any length. So, in your routing table, you will actually have this kind of information. You will have the network address followed by the prefix, and you will specify the next hop. So, what will actually happen is that every network now is actually represented as a pair, right, as a value and length pair. And what we look for is a longest prefix match. That is, this number here actually is giving us an identification of what this mask refers to. Okay, this is a 24-bit mask that needs to be applied, and we use the same masking procedure, which is a bitwise AND with the given network address. So, when a destination address, when a packet arrives at the destination address, you pick out the destination address, you apply this mask with whatever prefix number you have, right, with this mask, and you check whether it matches this corresponding network address. If it matches the network address, then you send it to the corresponding next hop. Okay. What is important here is that we need to look for the longest prefix match, because as we saw, you could have situations where it matches more than a given address may match more than one prefix. Then we always look for a more specific match. Okay, so that is one thing. And by doing this, using this kind of CIDR routing, you will also see that you can aggregate routes in a better manner. Okay, to quickly go through an example, right. So, if I had a packet which comes with 128.96.39.10, where would it go, right? So, I apply this 24-bit mask, which is 255.255.255.0, and when I do the AND operation, what will I get? I will get 128.96.39.0, right. So, it matches with the interface 0. So, it will have to go to interface 0, right. So, this is what will happen. Now, this is another quick example to understand how the route aggregation will take place. If you look at route aggregation, let us look at what we have. Let us say for instance I have different customers who have these addresses 128, 129, 130 all the way up to 135. The first 8 bits are common. Now all these now actually can be grouped together. See, look at this, they have 128/24. This is again 129/24, which means only the last 8 bits are used as the node part of the address. So I can aggregate all these together because they are all contiguous addresses and treat them as a single entry, have only one address advertised, combining all these 8 different things as 128.112.128/21. Now why 21? Because you can see there are 8 different things which are grouped together. So and they are all contiguous, right? So the first, so you can see that the last 3 bits here, right, out of this address, they will all be common, right? They can be masked out, and therefore I can specify, or rather the first 5 bits of this bit will be common in all of them. The last 3 bits are where it differs. So those last 3 bits are masked out, and you choose only the first 21 bits which are the common part of the address and use that to identify all these networks as belonging to a single block. Okay, that is what we are able to specify using this. Okay. So, so if you look at our IP forwarding with the CIDR prefixes, you can see that your network now, network addresses can be of any length from 2 bits to 32 bits, right. The prefixes can be of any length. So this is important to note. So as I said before, we can have prefixes in the forwarding tables that overlap. Okay. So for instance, both these addresses 171.69 and 171.69.10, this has 16-bit prefix, this has a 24-bit prefix, can exist in the router, and a packet which is destined to this address 171.69.10.5 will match both. So which one do I choose? I choose the one which is more specific. Which is more specific? The one which has the longest match is more specific, so you will match it with this address, right. So this is basically what you will do. But if you take an address which is 171.69.20.5, it will not match this address, but it will only match 171.69. So you will be able to identify exactly which network this particular packet has to be forwarded to. Okay. So this is what you will see. So this is again yet another example of your route aggregation that we just saw. So you can see that I have again here 8 different addresses being aggregated and sent out as a single address. So this is the way in which the aggregation can be done. Okay. Yet another important topic when you talk about the IP address repletion problem is the network address translation problem. Okay, or the solution rather to this address exhaustion problem is a network address translation. So what is network address translation? All of you would have heard about this. Basically what we try to use is, we try to use one common address for an organization and share it among multiple nodes which are there in that particular organization, and you do a translation from all addresses to that particular single address. So how do we do this? Basically what we do is we use private IP addresses in this range, at the 10 dot series or 172 series or 192 series. Okay, and these are the private addresses which are used on a institution side or on the network side, and what is exposed outside is only one single address or just a small set of subset of IP addresses. Okay, and what the network address translation basically does is, it will take these addresses and map them to the corresponding address, the corresponding address that has been assigned. Now why do we do this? This basically is that you do not need to get, if I have 256 nodes, I do not need to actually get 256 different IP addresses. I can only get one or a few IP addresses and share it among my different 256 nodes that are there in the network. Again, another short term solution to handle this problem of the IP address space getting exhausted. Okay. So, so basically what we do here is that the local network will just have one IP address as far as the outside world is concerned. I do not need a range of addresses to be got from the ISP, okay, that is our advantage, and you can change the addresses of devices in your local network without notifying the outside world. Okay, that flexibility we get. You can also change the ISP without changing the addresses of devices in the local network. So we have these advantages. Okay, it gives us a lot more flexibility in handling the these different addresses that are available. Okay, so this gives you an example of what would actually take place. So if I have, for instance, this is my local network, home network. I have different addresses 10.0.0.1, 0.2, 0.3, which are all private addresses that I am using here, connected to a switch. On the other side, which is visible to the rest of the network, I have a proper say class B address 138.76.29.7. Okay, now this is the IP address that is exposed to the rest of the world, and inside these are the addresses that are used. And what happens here in terms of the network address translation is that this address, okay, the different addresses over here are mapped to this address. Now how do I map this address? There are again different techniques which are used for it, for that purpose. Okay, we basically use different port numbers. Okay, you do a mapping of port numbers or there are different, in fact many different schemes that are used. So, port number mapping is one of the common techniques which is used. So, using a port number mapping technique, you can actually map these addresses and provide only a single IP address for the rest of the world. So, we will just take a look at this NAT example that will explain what we are talking about. So, for instance, when a host from here, okay, sends a particular packet, it sends a packet to a particular data to a particular destination address on a port number. At the NAT table which exists at the router, what will happen is that there will be a mapping that is done. The LAN side address 10.0.0.1 at some address at port number is mapped to a WAN side address which is 138.76.29.7 at a different port number. Okay, and so this is what is sent out on this side. Now, when a reply is obtained from the other side, it will come to this address, and again at the router in the reverse path, this address here will be mapped to this LAN side address, and it will be sent to this correct device that is over here. Okay, so using this kind of a mapping, right, having a table in between which is able to do this mapping, this address translation is done, and we find that this is a common solution which is used in many networks. So, we need to be aware of this network address translation as a mechanism. The only problem with NAT is that it is a little controversial, because we are kind of routers are only supposed to process up to layer 3, whereas we are changing port numbers and so on. We are actually interfering with the normal layered mechanism. So, that is one of the disadvantages that we normally have with NAT, but nevertheless it is still quite popularly used. Okay. So, to summarize what we have looked at in this module, we have looked at subnets, we have looked at subnet masks, we have looked at classless addressing, why it is needed, and how it fixes the scalability problem, and how CIDR prefixes are determined, and how it can be used for aggregation. We have also briefly touched upon NAT. So, thank you.